Hello everyone. In this video, I will try to explain the implementation of neural network in C++, and we will look at how different learning rates impact the error and convergence, and also how number of iterations impact the output. Alright, so we will be creating neural network code for this particular model shown. These are the weights, these are the biases, the inputs and the output. So one important thing to remember is that we will be using matrix algebra to solve this. So I'll just give you a brief example so that when we run over the code it is easier to understand. Okay, so look at these set of weights and look at these set of inputs. So these set of weights multiplied with these set of inputs to compute net h1, and then it is squashed using the sigma to compute output of h1 and h2 respectively. So this is our weight matrix. So suppose I denote, this is our weight matrix and this is our input matrix. So we matrix multiply it, and this multiplication is possible. So this is 2 cross 2, this is 2 cross 1. The final output will be 2 cross 1, 2 rows and 1 column. So when we multiply it using matrix etc. So 0.15 multiplied by x1 plus 0.20 multiplied by x2. So this is our this thing we get when we multiply it, and similarly when we multiply. So this is essentially what we get. When we add bias term to it, so it becomes net h1 and h2. So you can actually keep the value of x1 and x2 and just use the variables here. So adding bias, this is what we get as the net h1 and h2. So this is how we compute how input multiplies by the input and hidden layer weight gives us the output through matrix multiplication. So this is exactly what we will do in our code also. So when we add biases, we get net h1 and h2, and then to get the output, we squash it using the sigmoid function. So this is the approach that we will be generally using multiple times. So now going back to our code, right? So here I have used the C++. This function is used for printing the two-dimensional matrix with height 1 and this one with height 2. So this is only for printing, just for checking. Alright, so this is the input. This is the input 0.05, 0.10. It is in form of a 2 cross 2 rows and 1 column matrix. Okay. I'm running it for 100 times, so I have created an error for array 500. So this is the weight from input to hidden layer. So 0.5. So these are the initial set of weights from input neurons to second in the hidden layer. And so row 1 shows weight from input neuron to the first neuron in the hidden layer. So both the neurons, that is 0.515 and 0.2. So from input x1 to w to hidden neuron 1 is 0.15. From input x2 to hidden layer first neuron is 0.20. This is also seen in the diagram. So from x1 to h1, this is w1. W1 is 0.15. From x2 to w, it is 0.20. So similarly, this is how it shows, and row 2 shows the weight from input neurons to the second neuron in the hidden layer. These are the weights from hidden to output layer. Okay, so essentially from hidden to output layer, these are the bias terms. These are the same for all the neurons in the hidden layer and output layer. And this is the learning rate. I'll just write here also. So this is the learning rate. Later we will change it. So now, for now, forget about this. This I actually added in the last to show the number of times I have to run this particular training code for neural network. Okay, so just runs 100 times. Okay, so in the first thing, I compute net H1 and H2. So the 2D array containing output of input neurons to the weights connecting input to the hidden neuron. So here what I do is I am basically computing the output of this multiplication. So I multiply this and get the result in the result two-dimensional array. I print it. Okay, and this is the net activation, but it's not the output. Please note that I'm also adding bias in the loop only. I'm not adding it externally. So after the multiplication is done, in the final thing, I'm adding the bias and I'm computing the net output H1 and H2 using the sigmoid function. Similarly, after I've computed the how output from input to hidden, now from hidden layer to output, I compute another set of metric multiplication. So in this time, the weights between hidden and output layer are getting multiplied with the output of H1 and output of H2, which is stored in hidden one output. So hidden one output is used for multiplication. So this is simple matrix multiplication. It's not very difficult to understand. If you spend time, you will understand. Okay, I'm also adding the bias term and then I compute the final output. Once I have the final output and I have the target output also, now I can compute the error. Error is computed as mean squared error divided by 2. So this is the error I get. Final output minus target output whole square plus final output, second output for final output, and then target output whole square. So there are two outputs. Two target outputs are there and two neurons are there. So there are two error terms which combine to form the error total. This particular value is stored in the index of error. So now here I am updating the weights. Although I have written the equations over here, and if the updating is more complex, we can write actually the matrix multiplication, but just to show here, I have written simple equations, and these equations are coming from what we had learned here. So these equations are nothing but I have written the formulas that we have derived over here. So it is good if you can go over them and try to verify. It will help you understand how things are working. So this is how I'm updating each of the weights. So here there is a twist that since we're updating weight from hidden to input layer, we require original weights. So we first update weights in input to hidden layer because we update weight from output to hidden layer. So they might get changed. So remember when we were updating weights, we started with D total by W5. So W5 was getting changed. However, when we change W1, W2, W3, W4, we require these weights. So if we in the code update these weights first, so these values will change, and then since these values are used for updation of W1, W2, W3, W4, it might be problematic because the old values are used in W1, W2, W3, W4. So first, what we do is in implementation, I have updated these set of weights first, and then these later. So this is the different change. So here I have simply updated the weights, and then later I have updated weight from hidden layer to output layer. So you just go through the code. I have also attached the code link in the description below. So this is my first iteration of weight update. Later on, I can actually store each of these errors in a CSV file, and then I will show you its analysis as well. Alright, so I'll just run the code for you. Okay. So it will go on for 100 iterations, and then after that it will stop. So these are the final updated weights from hidden layer to output layer, and updated weights from hidden layer to output layer. So this is how the program has actually run, and it is complete. Now I will show you how the error aspect is taken care of with the learning rate and with the number of iterations. What I had done was that in the same code, I had changed the learning rate. So it was 0.25, 0.50, and 0.75, and I wanted to understand how error, behaves as we change the learning rate. I had also changed the number of iterations, but essentially, it will show us only how many iterations are going on. Then I used, so I stored the error values for each of the unique learning rate into file by given by the error underscore number of iterations and the index of the learning rate. So 1 means 0.25, 2 means 0.50, 3 means 0.75. So when you are running this code, you can actually uncomment this and try to understand. Okay, so this is my R program. So what is happening here is that so this is my neural network folder. I have computed the errors and I have stored in these files. So error 50.1 means the error for neural network in which the number of iterations of 50, learning rate index 1, that is 0.25. This is 0.50, 0.75, and similarly for 100. So what I do is that I read this file and then I try to plot this. So if I run it, yeah, I will be sharing this code also so you can have a look. So what is happening here is that this is the total error of neural network. There are number of iterations. So as you can see, so my bad, I have not been able to show the index. So black one is for the first one, learning rate is 0.25. For red one, learning rate is 0.50, and for blue one, learning rate is 0.75. So as we can see that for a given iteration, so let's say for iteration 15, okay, here somewhere here, the error is least for this blue followed by the red and then. So that means this neural network with eta 0.75 is learning way faster and with black is learning a bit slower. So this is how this shows that how drastically the weights are updated and therefore error reduced. So this is just what learning rate usually talks about. If I do it for 100, I'm not sure, should have been there. But similar, we can deploy it for 100 also. I'll just show you once because I want you to contrast how things look different for number of iterations as 50 and 100. So if I run this code, yeah. So you see now we have much more data points and we can actually see that slowly it is converging. The important thing to remember is that with learning at 0.25, it slowly decreases down the list 100 iterations. So it takes 100 steps. Whereas when the learning rate is 0.50, it takes 60 steps to finally reach to the minimum error. And when the learning rate is 0.75, it reaches quite fast with number of iterations as 40. It is advisable to take small steps when learning so that we don't jump abruptly from maxima to minima and don't get caught up in local minima. So it is advised that we take not too high and not too low learning rate. So usually we take 0.50. So this was my brief attempt to explain to you the implementation of neural network in C++. And here I tried to explain you how the weights are getting updated. So I think that if you can yourself spend some time trying to do this on your own, it will be very easy for you to understand what exactly is happening inside the neural network. And next time when you work with neural networks, you will not just be playing with some code, you will actually be understanding intuitively what is happening inside the neural network. And that is very important. So that's all from my end. I will come back again with some more insights on machine learning and network, specifically in health domain. Thank you for watching the video. If you have any comments,